Okay, so last time we focused on set agreement, and this time we're going to talk about a much larger class of tasks, namely colorless tasks. So what do we mean by colorless? Well, for example, in the input to either consensus or set agreement, it's possible that any process can take any input. So there's no restriction on who gets what input. Now, you can imagine a task that says that blue gets odd numbers and red gets even numbers. But here, that's not true. It's also the case that not only can they swap inputs, but somebody can take someone else's input. And that's also perfectly good input. And the same is actually true of outputs for both of these. So examples of colorless tasks are consensus, where everybody's output, it's all the same output, so it's okay if they exchange. And the same is true for a set agreement. Here we have two set agreement, and it's perfectly okay to permute the.
The requirement is that if the input is swapped, then the output should be the same.
No.
The output is the same?
No, it says that if you run the task and everybody has their output, if you then swap outputs, so I throw mine away and copy yours, that's also okay. So that there's no, the output that there's some set of correct outputs and anybody can sort of pick and choose among them.
And also any subset of outputs?
Is a legal output, yeah. And so this is an informal definition. I'll make this precise in a minute. But the intuition is that the identity of the process doesn't matter. And anybody can take anybody else's input or output, and everything is still okay. Now, an example of something that isn't colorless. So many interesting tasks are colorless, but not all of them. So remember weak symmetry breaking, where the processes come in and we split them into two groups, is not colorless. Because if the red one decides to join the others, then that's not okay. So that's an example of something that is not a colorless task. But most of the other tasks that people worry about are colorless. So here's kind of an informal specification. So we'll start out with an input complex. Before, each vertex was labeled with a process ID and a value. But now we're just going to throw out the process IDs. So we'll have a colorless input complex. And we'll use a little star to indicate that this is supposed to be colorless. So complex without a star, everything is labeled with a process ID. And complex with a star, there are only values and no process IDs. So then what I'll do now is I'll talk about a particularly useful gadget that we can use to talk about these problems called a pseudosphere. So here's an informal specification of a colorless task. That is, we have a bunch of processes start out on a colorless input. And unlike the color task, it's okay if multiple processes start on the same vertex. Because this just means that they're starting out with the same value. So that you start out with one input simplex, whose dimension might be lower than the number of processes now. And the processes are kind of scattered among them. We have a relation that tells you if you start out here where you can end up. And so it says if you start out on sigma, then you end up on a big delta of sigma over here. And then everyone ends up on a simplex in this region. And again, it's okay if multiple processes end up on a single vertex, because that just means that they're taking the same value. So because the process IDs aren't important, we're going to throw them out. It's helpful to try to make this a little bit more precise. So here, for example, we're looking at the input complex for consensus. So here, P0 has 0. This simplex here represents all zeros. This represents all ones, and these are all the mixed ones. We've seen this drawing before. And what we're really doing is we're independently assigning binary values to each of the processes. So this idea that we have a set of processes and we look at all the different ways we can independently assign values to them from a set is going to turn out to be important. And the result here is a two-dimensional sphere. And this is true even in higher dimensions. You end up with a complex that's topologically the same as a sphere. So now,
can I ask,
yeah.
say, majority, also colorless? Non-colorless?
So majority meaning that you only...
I wanted to, so I have, say, zeros and ones, and I want to decide on the value that...
No.
Majority.
No, that's not colorless because the...
That's a more natural...
Yeah. It satisfies one requirement that anybody can... It's sort of colorless on the input because anybody can take anybody else's input, but the output isn't colorless.
No, not anyone can take. Because if we have a majority of ones and you have a zero, we can all take the zero.
Oh, well, that would change the output, but it's still a legitimate input.
Yeah.
So that, but on the output is...
That's that's an example of another problem which is not
Yeah.
Can you define formally what is colorless? I'm not sure.
Oh, so I haven't given you a formal definition yet, but the informal definition is that any input simplex says this is a possible set of initial assignments of values to processes. So if I take any one of those and I steal somebody else's input in place of mine, or exchange inputs with someone else, then that's still a legitimate input.
Does that mean that...
And what, it doesn't say anything about the output?
Well, the same is true of the output. So that if...
It has to be true for output and input?
Yeah.
Is output corresponding to the input?
Yeah. So that, so if I run the protocol and everybody picks a value, and just before I decide, I go over and I steal a copy of your value, that's okay. So this is example is set agreement. So we narrowed it down to k different values, and I have my value, and if I take someone else's value, it's still only k values, because I've taken I've taken a value from the same pool in some sense.
If you run the protocol with specific input values,
Yeah.
then you can steal your neighbor's value, and that's okay.
Yes.
That's okay.
Yeah.
Now I'm confused because now it seems like majority is colorless according to this definition.
Let's see. I guess on the output, so the output is what you think the majority is, but then the output, but everybody agrees. So yeah. So in that sense, it would be actually. I think it is colorless, because everybody ends up. I think 3 is the majority value, and you better have the same thing. And if we swap 3s, then that doesn't make any difference. On the output,
So if I start with some input, I can't just erase my input and take someone else's.
but that's another legitimate input. If
It's a legitimate input, but will the relationship between the input and the output? Will that
but that's okay.
depend on my real initial value?
No. All we're saying
So
is,
for example, if it's majority, you have a 0 and we all have 1s. If we all see that you have a 0 and we adopt a 0,
we're not saying if
it
you
will be 0 even though it's not the majority.
changing the input is okay if that changes the output. It's just that changing the input is still legitimate input.
So that doesn't, you don't change the input while retaining the...
Yes, so before we start the protocol, so the picture is everybody starts out with a value. Before we start the protocol, I can steal your value and then still run the protocol, and it's okay. If you require that everybody starts out with unique values, for example, you can't do that. So if the values are unique, I can't steal your value. But if the values are...
so essentially the input complex is like S to the N or something like that?
Yeah.
Set of values,
It's
the Cartesian product.
It's going to be spheres all over the place.
It's the Cartesian product of the set of values.
Yeah.
Everyone can have any of it.
Yeah.
You
But,
can have anything. Anyone could have any combination of...
yeah, well, I'll get to that in a minute. There are a few technical restrictions on that, but that's the basic idea.
So majority is probably colorless then.
I think majority is colorless. Yeah.
Okay.
Yeah. Say counting. Everybody takes a unique value from 1 to n is not colorless because I can't steal someone's output because the outputs have to be unique. Okay, so let's look at input to 2-set agreement. 3 values, 2-set agreement. So the question is how many ways can you independently assign 3 values to a actually this should be 2 values. Oh no, it's 3 values. Okay. So here we have 0, 1, 0. These are all the ways to do 0 and 1. This is what we saw on the previous slide. This is all the ways to do 0 and 2. And we glue those 2 edges together because they're the same. So we look at all the different ways of doing 1 and 2, and then we glue those edges together. So you end up with a kind of a ring of spheres. And so this is not exactly a sphere, but it's a lot like a sphere. So we're going to call it a pseudosphere. And this is a very common kind of structure that we'll see now, and we'll see it a couple times later on in the course. So let's define it. So this is the symbol for a pseudosphere. We have a sequence of m+1 simplexes and a set of m+1 process IDs. And so that's the notation that we'll use to represent a pseudosphere. And what does it mean? Well, each vertex has the form process ID and vertex, where we take a process ID from U. So process ID comes from here. And we take a vertex from if this is p sub I, then we take the ith simplex. So, there's a little bit of notation abuse going on here in that each p sub I is associated with sigma sub I. What does a simplex look like? Well, simplex is just a set of vertexes with the property that each vertex is labeled with a unique process ID. Because what I'm doing is I'm reconstructing a colored complex from the colorless complex. And each one has a each one has a vertex from S sub I. And these are all done done independently. So all the process IDs have to be unique, but this can be any vertex from S sub I. And I can change any one of these without changing any of the others. That's still a simplex.
From sigma sub I?
From sigma sub I, yeah.
So it's all the same sigma?
They could be the same sigma, and sometimes they'll be different. Okay. So in fact, if they're all the same sigma, we write it like this. And that's the most common case. But sometimes for inductive constructions, we'll need to have them be slightly different. So then what happens is that everybody independently chooses a vertex from sigma. And because these choices are all independent, this thing is highly connected. And if sigma has 2 elements, then this is an n-dimensional sphere. But if it has more, then it looks more like those rings of spheres all glued together. And in fact, we can take we can define it not just with a simplex, but an entire complex. So we can talk about the pseudosphere, taking the pseudosphere over a complex. It's just, you can think of it as taking a regular complex and kind of inflating it so that the vertices turn into spheres and so on. So their simplex is just unique process IDs, and these are vertexes from some simplex in C. So we won't use this very much, but it will show up. So these have some nice combinatorial structures, which are good for making inductive arguments. So the simplest one is that if each of these simplexes consists of a single vertex, then what you get is a single simplex. So if each of these are singleton sets, then the pseudosphere is just this single simplex. The other simplification rule is that if one of these slots is empty, then we can throw it away, and we just have to throw away the owner of that as well. So if in the course of a calculation we show that one of these components is empty, then we can throw out that simplex, and we can throw out its owner from a P. So what we end up with is we take U, we take out Pj, and we take out sigma sub j, and we eliminate it there. So that's a way of kind of cleaning up. So the other nice thing is that intersections of pseudospheres are pseudospheres. So they're closed under intersection. So here I have a set of processes U, set of simplexes, set of processes U, another set of simplexes. And then when I take the intersection of these two things, I get a pseudosphere over the same set of processes, but the choices are the component-wise intersections. And if any of these component-wise intersections turns out to be empty, then we can apply the previous simplification rule and throw things out. So you can, there's a lot of combinatorial stuff you can do with these things.
Meaning of equivalence?
Oh, this means that if you sort of rename the vertices, then they're the same thing. So there's some technicalities where the labels might be different, but it's really the same thing. Because you end up erasing things. And
Isomorphism.
yes, yeah, isomorphic. Then we're also, so I've talked about how you take a complex and build up sort of pseudosphere over it. You also want to go the other direction sometimes. So we have a simple projection operator that takes a pseudosphere and gives you back the complex, and it just takes each vertex and throws out the process ID. So it collapses it back down. And that'll be handy sometimes. Okay, so now we're ready to give you a formal definition of colorless tasks in terms of the definition of tasks that we had before.
You cannot know how the complex looks like. If you have the pseudosphere, you don't know what the simplexes are in the complex C.
No, but every vertex is labeled with a process ID and a vertex from this other complex.
Right. So then you can know which vertices are in each complex.
Yeah,
but
yeah.
you can't know the structure of the complex.
Well, you know the structure because when you define the pseudosphere here, so the pseudosphere is sort of given by this process. You take a process ID from here and a vertex from there. And then, so it's sort of, since this definition, this construction has this complex in it.
So you assume that C is M plus 1 simplexes?
Yeah. So the, well, no, this could be any dimension. So this could be much smaller dimension than this. I mean, I suppose it could be bigger too, but we don't care so much about that.
But process PI, it comes from a vertex from where?
From so here. So what we did first thing we have a simplex. We defined it over a single simplex, where everybody just independently picks a vertex from here, and so the size of this determines the dimension of the pseudosphere complex, but this can be different cardinality than the dimension of this.
Right, but here it's a simplex, so you know that these are the vertices of
Yeah.
the simplex. But if it's a complex, how do you know how the simplex
So you're given this complex, and the rule is that these all have to come from a single simplex in C.
all of them has to be from the same simplex?
Yeah. But it can be a big simplex or a small simplex, and everything glues together because you could have two simplexes in here that say share a face, then the resulting things down here will also share a face. So the structure of this is still kind of implicit in the structure of C is implicit in the structure of the whole thing. And this gives you a way to recover the structure of the original complex based on the pseudosphere. Okay, so here's our formal definition. So a colorless task specification is given by an input, colorless input simplex, a colorless output simplex, and a relation, which is I'll explain what this means later, but this is a kind of relation that preserves intersections that sends each input simplex to some subcomplex here. So this is basically the same definition that we used for tasks before, except now everything is uncolored rather than colored. And what does this mean? Well, we can translate it back into our familiar terminology. And what we're doing is we take the we put pseudospheres around the input complex, around the output complex. Pi here is the set of all processes. So basically, this is colorless, so we add color by copying each of the vertices and then applying. Because it's a colorless task, we can sort of apply these things independently to all the pieces. And what does this mean? Well, each process independently takes an input vertex from the simplex. So this is the simplex of values, and each process independently picks a color, but they have to be a color, or sorry, they take a value, but the value has to be from the same simplex to ensure that they're compatible. But this captures the idea that anybody can steal anyone else's value because it leaves you on the same pseudosphere. And anybody can, you can swap values because that also leaves you on the same pseudosphere. Then the same thing happens for the output complex. So the relation here, I mean, I won't spend a lot of time on this, but basically it does what you want. You start out here and you have a relation there. If you pull that up, if you pull that back upstairs to the pseudospheres, then you get take the map that commutes here. So this is, this diagram just says that it does exactly what you would intuitively expect it to do. Yeah, pi is the projection that discards these things. So you can't go the other way because the other way is not a function, but this is a function. Okay. So one nice thing about pseudospheres is that if you look at a weight-free read-write model and you run any protocol on a pseudosphere input, what you get remains connected. So pseudospheres are highly connected, and we'll prove that later on. But the interesting thing is for weight-free read-write protocols, the image of a pseudosphere under the protocol remains connected. And so this will be useful when we want to prove things about weight-free computation. So the protocol complex basically preserves the connectivity of your input. And since the input complexes for colorless tasks are pseudospheres, this is going to give us a way of looking at colorless tasks in weight-free read-write computational models. So how do we prove this? Well, we'll do this by structural induction. So I'm going to define a partial order on the simplexes of the pseudosphere, or on sets of simplexes, or sequences of simplexes, if each one of these things is a subset of the others and one of the inclusions is strict. So I'm going to induct on the size of the set of processes, which is the dimension of the pseudosphere. And there we have this partial order on the sets of processes. When, in the base case, there's only one process. In that case, u minus 2 is minus 1, and minus 1 connected just means you're not empty. So this is a easy thing to show. And then it's easy to see that if you take a pseudosphere over a single vertex, you assign it, you look at all the different ways you can assign values to that. It's a discrete set of points. You run any weight-free read-write protocol on that input, what you get is non-empty. So this is why we say something that's minus 1 connected is non-empty, because it makes these inductive arguments work. And non-empty means it's minus 1 connected. So all the arithmetic works out right. Okay, so let's go to the induction step. So now I want to show that this is true when I have n processes. And the hypothesis is that if I take the pseudosphere over n processes, and I'm choosing from each p sub I takes a vertex independently from each one of these, and then given that as the input complex, I run a read-write protocol, I can assume that this is n minus 2 connected. So now I'm going to do structural induction over these simplexes, using this partial order that I defined before. So the base case, each of these simplexes is a single vertex, because that's the that's minimal with respect to this partial order. And we know that this is a single simplex. Actually, this p shouldn't be here. So there's a bug on slide 35. So ignore this P. The pseudosphere here, we know is just the single simplex. And we know that applying P to a single simplex is n connected because of what we did the last lecture. So now we're going to continue. So now we're going to do the induction step for the partial order. So we did the base step for U, we did the induction step for U, we did the base step for the partial order, and now we're going to do the base step for this. And this is our induction hypothesis for U equals n that we can use. I'm reproducing it here. So then the hypothesis is that this is n minus 1 connected for everything that's strictly less than the set of simplexes we're looking at. So we want to figure out what's going on here. So what do we know? Well, we know because we're no longer in the base case, these cannot all be singleton sets. Somebody has to have at least 2 elements in there. So we pick sigma sub I, which has at least 2 elements where the index set is larger than 1. So this is where we were. So I'm going to apply the nerve lemma here. And so what I'm going to do is I'm going to define this sort of write k sub j as I'm going to take every individual vertex here and I'm going to put it in slot j. So I'm going to replace the entire simplex with a single vertex and take the resulting pseudosphere and call that k sub j. And the idea here is that this is a cover for the whole thing. So if I take the union of each of these things, then that's going to give you everything in here. So once we have a cover, we can start applying the nerve lemma. So the question is, what are the intersections of the k sub j look like? So we know by the induction hypothesis that k sub j is n minus 1 connected. That's the induction hypothesis for the partial order, because this is less than, that sequence is less than that by inclusion partial order. Okay, so remember we defined the k sub j. And so in order to apply the nerve lemma, we need to look at the intersections of these things. But these intersections are pretty easy to deal with. So here we, L sub j is the intersection over some index set j of the protocol applied to the pseudosphere over U of these sets here. Now, the protocol complex is what's called a carrier map, which means you can move the intersection inside. That what does it mean to, if I have 2 input simplexes, running the protocol in the intersection means that basically I fail everyone who's not in the intersection and I run there. If I run it on one and run it on the other and then take the intersection, I'm saying, well, what's the subcomplex where you can't tell the difference? Well, it's the ones where they failed before they told anyone what was going on. So they're the same. So we move the intersection here. Now, because pseudospheres have this intersection property that we looked at, we can move it all the way over here. But each of these is a distinct element. We have a bunch of singleton sets with distinct elements, and we take their intersection, it's empty. So what happens is this circumflex here means throw it away. So I can throw away process P from this set, throw away this vertex. And now I'm applying the protocol complex to a smaller dimensional pseudosphere. This set is smaller. So this is n minus 2 connected by the induction hypothesis for U, which means, if you do a little bit of arithmetic, that this is at least this connected. Remember where J is the cardinality of the index set. And this looks a little funny, but this is what we need to apply the nerve lemma. So this is actually much lower than the actual value, because J can be big, but we proved it's true for n minus 2. So this is kind of overkill. So remember the nerve lemma says because each k sub I is n minus 1 connected.
Can you go back to tell us to remind what J is?
Oh, J is an arbitrary index set. So J is any set of processes. Because the nerve lemma says that for any index set J, this is true. So what this is a review of what the nerve lemma says. So this says that we have this cover of k sub I, and if we know this is n minus 1 connected, and each of their intersections is n minus j connected, where j is the cardinality of this set. So every time we take bigger and bigger intersections, the connectivity shrinks by a dimension matching the size of the intersection. So if we can show this is true, then it's a fact that the entire complex is n minus 1 connected, if and only if its nerve. Actually, this should be n minus 1. If and only if its nerve is n minus 1 connected. So that's a review of the nerve complex, which we rolled this out of the closet and we're about to fire the cannon. Okay, so what's the nerve? Well, remember the nerve is a complex. The nerve of a cover, the vertex of the nerve is each of the covering sets. And a simplex are sets of covering sets that have non-empty intersections. But here, each Lj we've shown is this complex here, which is non-empty. So in fact, every intersection is non-empty. So that means that if we take another index set I, and we let j go over there, then then the nerve of that covering is a I minus 1 simplex. So the nerve is just a big simplex. So it has a very simple structure, which is n minus 1 connected, because it doesn't have any holes, which completes the proof that the result of applying the protocol complex to any pseudosphere is n minus 1 connected. So basically, we did a double induction. And this is a technical lemma that we can roll out again and again, which is why I wanted to go through this. Okay, so in order to keep the notation from being cluttered, I'm going to write P of I star instead of a P of the pseudosphere. But this is what it means. And I can restate this theorem using the more compact notation to say that for every colorless simplex in the input complex, the result of applying the protocol complex to that simplex is n minus 1 connected. So this is, we did the same thing for colored simplexes last time for for weight-free read-write computation, and now we just did the same thing for colorless simplexes, and for colorless tasks. Okay, so now what I'm going to do is I'm going to give you the basic theorem that tells you when you can and necessary and sufficient condition for solving any colorless task in a read-write memory. Okay, so this says I've given you a colorless task, and I've defined what that means with the pseudospheres and so on. But I think the informal definition I gave you at the beginning is the one you should keep in your head. So this has a weight-free read-write protocol, in shared memory, if and only if there is a continuous map from the polyhedron, that is the point set occupied by the colorless input complex, to the colorless output complex. So if I can take the input complex and continuously map it into the output complex in a way that respects the task definition, then there's a protocol. And if there's no way to do this, then there is no protocol. So that says that in some sense, the structure of the input is the continuous. There's a continuous image of the input in the output matching this delta. And really, that weight-free read-write computation can't really change the topology of the input complex in a significant way. Because if you take a continuous image of something, then the image looks a lot like the original. You can't tear holes into it or do anything like that. So I'm going to prove necessary and sufficient conditions. And the first direction, I'll say, suppose that we do have a weight-free read-write protocol. I'm going to build a continuous map. So what that looks like, that's a lemma that says that if there is a weight-free read-write protocol for this, then there is a continuous map from the input to the output. So let me remind you the definition of a skeleton. So we, given a complex C, the skeleton is just the set of simplexes, the complex determined by the simplexes of dimension k or less. So here 1 or less, and here 0 or less. And so given the protocol, we construct the map basically as follows. The proof strategy is that I'm going to build up this map inductively on the skeletons. So I'm going to start out by defining the map on each individual vertex. I'm going to extend the map to edges, going to extend that to solid triangles, tetrahedra, all the way up to the top. So this D is the dimension of the skeleton. So the base is easy, because this is just the set of vertices. And I'm going to, we know that the image of any vertex is non-empty, so I'm just going to choose any vertex in there. So this clearly matches delta. Well, this will match delta when we go. So I'm building this map into the protocol complex, and then later on I'll map from the protocol complex to the output complex. So we're building the maps between the different, slightly different complexes than the ones we're ultimately interested in. Okay, so now the induction hypothesis is that for the D-1 skeleton, I have a map that sends each simplex into its image under the protocol complex. So I have a continuous map that sort of agrees with the task definition. Now, what do we know? Well, we know that for every colorless simplex in the skeleton of the input complex, this sends that to the protocol complex applied to the actual simplex. So this says with the colorless, G is defined on the skeleton, but the space it maps into is the image of the entire simplex. But we also know that this is D-1 connected from our earlier theorem. So in other words, there is no hole here that would prevent us from extending this up 1 dimension. Because the skeleton of a single simplex is topologically a sphere. And the meaning of being connected is that if you have a continuous map of a sphere, you can extend it to a map of the disk. And since the boundary of the simplex is a sphere, and the simplex itself is a disk, topologically speaking, we can extend the map up 1 dimension to the D, to dimension D. And then if you look at each of these things, they all agree on their intersections, which is the D-1 skeleton. So this gives us a coherent map from the D skeleton all the way in here. So we've just extended this up 1 dimension. And so what we built is a continuous map that takes the uncolored input simplex to its, actually this should be a polyhedron. That's another about 57. So this should be the polyhedron for the input simplex to the polyhedron of its image under the protocol. Okay, so now remember that what does it mean to run a protocol? Well, you run the protocol, you gather all this information, and then you apply a decision map, little delta, that says that this is what I saw. This is the value that I should take in response to that. And so you can turn that into a continuous map by this barycentric extension, where I just take the, this is defined on vertices, and so any simplex spanned by a bunch of vertices, I just take look at all the, take the barycentric coordinates of the whole simplex and turn that into a continuous map. So that gives us a continuous map from here to here. So now all we need to do is compose this map and that map. And that gives us a map from a continuous map from the colorless input complex to the protocol complex carried by a delta star.
So you always have a continuous mapping from the protocol complex to the output complex?
Yeah, well, we always have a simplicial map because when you look at your output, then that says if you sort of get rid of, if you go back to the colored version, then there was, at the end of the protocol complex, you have your entire history of your computation, which is independent of any particular task. And then all the task-specific knowledge is hidden in the definition here. So I look at this long computation and I say, oh, I should decide 27 as a result. So that gives you a simplicial map. But a simplicial map is a combinatorial object. You know, it maps vertices to vertices and simplexes to simplexes. But we want to turn this into a continuous map. So what we do is we say, okay, I'm going to take this simplex and sort of fill in the interior. Every interior point is barycentric, has barycentric coordinates in terms of the other vertices. So I'm going to basically do the same thing on the other side and carry every internal point into its barycentric, the point with the same barycentric coordinates. Okay, so this is one direction of the proof. Now, the next I want to show it's sufficient. So what I want to show is that if I have a continuous map, I can build a protocol. And so what that looks like is just this. If there is a continuous map from the polyhedron of the colorless input complex to the polyhedron of the colorless output complex, carried by the task definition, then there's a read-write protocol for the colorless task. So to do this, we need another trick, which we'll call barycentric agreement. So this is an actual algorithm. So the idea is I'm going to start out with the input complex is just some complex. I've drawn it as a triangle here, but it could be an arbitrary complex. And then I'm going to take the barycentric subdivision, which looks like that. And the rule is that a bunch of processes start out on the vertexes of some input simplex. And again, you can have multiple processes on any vertex. So the number of processes and the dimension of the complex are independent of each other. So they all start out on some input simplex, and they have to end up on the vertices of some input simplex of the barycentric subdivision. So it doesn't have to be the same dimension. It's okay if they all go to the same vertex. You know, it's okay if they go to an edge, but they have to end up in the subdivision of what they started out on. And so given that, that's a tool that we can use for other things. Okay, so here's a simple protocol. So the idea is each process starts out and they have an array in a memory, and you write out your ID. You know, you write out the vertex where you started to shared memory. So here, Red, said, I started out on V0. And then you take an atomic snapshot. You know, we know how to take atomic snapshots of memory. And so Red says, I saw this vertex. Okay, then another process wakes up and it writes its value here. It started out on V2. Then it takes a snapshot. And so what it has now is an edge of the input simplex. And when we continue this way, we have a sequence of faces of the input simplex where everybody started out on. And so the key point is that each view that everyone saw is a face of the input simplex, because each one is discovering more and more starting positions for different processes. But by assumption, everybody starts out on the same simplex. So what you're going to see is a face of the one that you saw. And it's okay if different colored processes start out on the same simplex. It still works because we just throw out the duplicates. And so this process sees only one vertex because it went first. This one sees an edge of the input simplex, and this one sees the entire thing. Now, what's important here is that because snapshots are atomic, the views that the processes have are contained in each other. This one is contained in that, is contained in that. And you remember the combinatorial definition for a barycentric agreement is that it's a chain of faces ordered by inclusion. And so what happens here is that each of these is a vertex of the barycentric subdivision. You just go to the barycenter of the face that you saw. And because the original views were ordered by inclusion, it turns out that altogether they span a simplex of the barycentric subdivision.
But they're ordered by inclusion just in, because the snapshot is atomic.
Yeah. If the snapshot were not atomic, this wouldn't work. But
so here everyone writes most ones.
Yeah. So if you want to do iterated barycentric, if you want to do convergence on the iterated barycentric subdivision, you need to do it multiple times. But if all you want is a single barycentric subdivision, then you write once and take one snapshot, and that's it. And in fact, we do want to do multiple barycentric subdivisions. So you take n iterated barycentric subdivisions. I was too lazy to draw them everywhere, so they're drawn here. And you want to converge to some simplex of that, you can do that in n rounds, big N rounds. Okay, so now I'm going to show you how we can go from a map to a protocol, given all of that machinery set into a place. So here's our input complex, here's our output complex, and you can see that they're colorless. And the assumption is that we have a continuous map that carries an image of this over here, and that this respects delta, the task definition. And so say these vertexes are the image of these things here. So what I'm going to do is I'm going to take a simplicial approximation of this map. So you remember, given a continuous map from one complex to another, we can always come up with a simplicial map that approximates it, but we might have to do subdivision over here in order for everything to work. So given this continuous map, I'm going to take a simplicial approximation, and in fact this will be a barycentric subdivision, possibly many times over. And that will give me a simplicial map that goes from here to here. And the important thing to prove, which I'm not going to do because it's fairly straightforward, but would take a couple slides, is that if the continuous map F is compatible with the task specification, so is its simplicial approximation, because they're so close. Okay, so now we can turn that into an algorithm by saying I have this simplicial map phi on this should say barycentric subdivision of I instead of I. So we can mark a bug on 71 and 70. So given this, everybody starts out on the simplex. They run barycentric agreement on the input. Then they apply phi of the input, and they end up on a simplex over here. And that's your algorithm. Beg pardon? Oh, so the map phi is defined on the subdivision of the input complex. You start out on an input simplex. Oh, the problem definition just says that everybody starts out on the vertex of an input simplex. So we've constructed a simplicial map, unfortunately not from the input simplex, but from a barycentric subdivision, possibly an n-fold barycentric subdivision. And so we can't apply phi directly because you would end up in you wouldn't end up on a simplex. So you've got to get everyone to sort of jump to a smaller simplex down here. Oh, that's the barycentric agreement protocol. So that was back here. Remember, we had this protocol where everybody sees a view. They, you write, take a snapshot. And so what that does is that guarantees that everybody ends up on a face of the barycentric subdivision. On the same, yeah. So everybody started out on a corner of the big simplex, and then they ended up on a corner of a small simplex in the subdivision. And so that's just an algorithm that says that, you start out on a simplex, subdivide it, I want you to converge onto one of the pieces.
No, I was wondering whether it solves a set agreement. Okay, it doesn't solve because you don't know what simplex you are.
Yeah. So this is something, this is something you can do with read-write memory. So with all this emphasis on case set agreement and so on, you might think that there's nothing you can do in read-write memory, but there actually are lots of interesting things, some of which we'll see later. And one of them is barycentric agreement. So you can take a subdivided simplex, and then you can write a read-write algorithm that has everyone converge onto one piece of it, onto the vertices of the simplex. So what we did was we start out with a continuous map. We take a simplicial approximation. And then we use barycentric agreement to end up to have everyone who started out here on a small simplex of the barycentric subdivision. And then we apply phi to have them converge on a simplex over here. And so the algorithm is you run n rounds of barycentric subdivision here, and then you jump over there. Now, there's an interesting thing here is that, have I actually given you an algorithm or not? I've certainly proved, I think, that an algorithm exists. But, if I told you the next homework is to go and write this algorithm, you might have trouble because, how do we know that this exists? Well, because it's the simplicial approximation theorem. And the simplicial approximation theorem says there is some n where if you subdivide enough, then that will give you then the simplicial map exists. And the complexity of this algorithm, the number of rounds you need to run, is equal to the number of subdivisions you need to do to get a simplicial approximation. And if you look, inside the engine room of the simplicial approximation theorem, this involves Lebesgue numbers and other kinds of stuff that I'm not going to talk about. But trying to figure out what the complexity of this algorithm actually is still an open research problem all these many years later. So coming up with a nice way of saying, given a problem, here's how to characterize this complexity is something that nobody really knows how to do.
Is there any update?
I suspect it's probably something like it's logarithmic in the, the problem is that even if you look at how the simplicial approximation theorem is proved, it's based on, it said something called the Lebesgue number, but the Lebesgue number is a function of how this complex is embedded in space. And I can take I can take isomorphic complexes, embed them into space in different ways with different Lebesgue numbers. So I can pick a really, really bad embedding with a really, really small Lebesgue number, and then it's basically the log of the inverse of the Lebesgue number is roughly how many rounds you need to run. And so that would be a really inefficient algorithm, but if I had a different embedding, I could get a much better one. And so nobody has ever sort of gone through to the end of this and said, here is a way to characterize what the inherent round complexity of an arbitrary problem is, even in terms, especially in combinatorial terms, because in order to get there, you have to go through this continuous theorem where everything depends on the specific embedding that you choose. So it's not easy to get a handle on that. So that's probably one of the big open research questions in this kind of area is can you say something interesting about the complexity other than there exists an n. Okay, so this completes the construction in the other direction. So what I've done is I've given you a particularly simple characterization of when you can solve a colorless task. It says that in weight-free read-write memory, at least, there's a protocol if and only if delta is compatible with the continuous map of the input complex to the output complex. And again, this is a generalization of, say, the impossibility proof for set agreement. Because set agreement, basically, the output complex has a hole, the input complex doesn't, and there's no continuous map that wraps the boundary of a hole, that wraps the boundary of a solid region around a hole. So this is sort of yet another level of generality there. So what I'm going to, we'll take a break now. So what I'm going to do after the break is I'm going to talk about, well, what happens if I give you read-write memory and the ability to do set consensus on the side. And that has a nice generalization because then we start talking about skeletons instead of actual complex. And then I'm going to ask whether we can, the problem whether tasks are, have solutions, whether that's decidable or not. If it's decidable, then that's good news because we can save a lot of money by firing all our grad students because we don't have to get them to write papers in the subject. We can program a Turing machine to crank out PODC papers. So, you know, if you come back later, you'll find out whether, you know, grad students will have a job in this area.